Now we want to use the method of separation of variables where the function psi, the wave function, is split into a product of two functions psi naught and f, where psi naught or psi 0 depends only on x, the position of the electron, and f depends only on time. We have to substitute this expression into the Schrodinger equation and see what happens. Now let's do that. The left hand side is I h bar d psi over dt there will just be psi 0 times f dot, where f dot is the derivative with respect to time of the function f. And here I'm just using shorthand to denote psi 0 of x times df of t dt. So that's what I mean. Okay, so the derivative only acts on the function f on the left. Whereas on the right we have h hat, so it's the Hamiltonian, which only acts on psi 0. And then I can multiply by f, because the Hamiltonian only depends on, only contains the spatial variable. If you take a look at the expression for the Hamiltonian, so let me write it down here. H hat is going to be, it's p squared divided by 2 mu, where mu is the reduced mass of the system, which is approximately equal to the mass of the electron, minus z e squared over r. And p squared is equal to minus p is equal to minus I h bar, the gradient. So this is p. So p squared will be equal to minus h squared del squared. Okay, so you see that there is this del squared which will act on the function psi 0, but it will not act on the function f. So the Hamiltonian here is not dependent upon time, so it does not depend on time. And this is important because in this case I can rewrite the expression that I have here like this. So I can divide by f, and I can divide by psi 0 on the left. So here I can of course divide by psi 0, but I cannot do it. So I cannot put this psi 0 before the h bar operator, for example. So I cannot move it freely, but I can divide by psi 0 here. So let me try to clear this out. So I have I h bar psi 0 f dot, and I will divide this by psi 0 times f, and the same on the, I can do the same on the right hand side. So I have h psi 0 times f divided by psi 0 times f. So I can simplify this f here with this f, but I have to be careful because I cannot do the same for this psi 0 here. So I cannot cancel them. This is not possible because I have to consider h bar times h bar acting on psi 0 as just one expression, right? Because h bar contains a Laplacian, and therefore it will act on psi 0 and it will change psi 0. And I cannot simplify these two expressions here. But I can do it on the left. Here I can simplify psi 0 because there is no operator that acts on psi 0. Okay, so from here we get that I h bar f dot divided by f is equal to h acting on psi 0 divided by psi 0. This is important now, because on the left here we have a function depends only on time. So this function depends on time, on the time variable t. Whereas on the, so this is on the left, whereas on the right we have a function that depends only on space, on the spatial variables x, y, z, or if you want to be more concise, on the vector x. And x and t are two, x contains three variables, but the vector x and the variable t are two independent quantities. They are independent. Okay, this means that I can change t But if I change t, only the left hand side could change, whereas the right hand side should not change. But since these two should be equal, this means that, of course, this is equal to a constant, right? This should be equal to a constant because I can change time, but this quantity here will not change. And therefore, since there is an equal sign here, it means that this quantity should not change as well. And therefore, here we have a constant. And the same thing if you change x, this quantity here in principle could change, but it is equal to a constant, sorry, it is equal to a quantity that does not change because it depends on time, and t and x are independent. Therefore, this must be equal to a constant. And I will call this constant E, which is the energy. This is the energy eigenvalue. Why is it energy? Well, you can see it from uh, a simple observation, for example, of this quantity here. We have the Hamiltonian, which multiplies psi 0 divided by psi 0. The Hamiltonian is energy. It has dimensions of energy, therefore this should be energy. But you can see, you can derive the same units from here as well, because h bar has dimensions of energy times time, and f dot divided by f has dimensions of 1 over time. So if you multiply energy times time divided by time, you will get energy. Okay? And that's pretty simple. But now we have two equations. We have an equation that's derivable from here, which tells us that I h bar f dot is equal to E times F. And we have another equation from here. So we can rewrite the other like this. H hat times psi 0 equal to E psi 0. These two are very important equations. In particular, this one that I have just framed, it is very, very important because this is the time independent Schrodinger equation. Whereas the starting equation, and I'm referring actually to this one, this is the time dependent Schrodinger equation. And this other one here, it is probably the least important here, because this equation here, it is pretty straightforward to solve. It is just, so if, for example, you can solve it like this. You have I h bar df over dt, then you can multiply by dt, so you have E times f times dt, and you can divide also by f, so you can rewrite it like this. And from here you can write df over f equal to E times dt divided by I h bar, or just minus I E dt over h bar, because I is also equal to minus 1 over I, right? Because I squared is equal to minus 1, and therefore I can of course rewrite it like this. So 1 over I is equal to minus I. So I could have written it like this: minus I is equal to plus 1 over I. Okay, and then from here you get that the logarithm of the function f should be minus I e t over h plus some constant. And you can easily see that this equation can be written in this form. If you exponentiate both sides, f of t is equal to some constant f0 times e to the minus I e t divided by h bar. So this is just the solution to this time equation here for f. But this is a very simple equation that doesn't tell us much about the solution to the Schrodinger equation. What we are really interested in is in the time independent Schrodinger equation. This will tell us much more about the energy. It is like the stationary part of the Schrodinger equation, whereas the dependence upon time, when we have a Hamiltonian that does not depend on time, can be always written like this. So we have an exponential which depends on time like this. We just have to multiply the stationary part, which is psi 0 here, by this exponential. and f0 is just a constant. It doesn't really matter, because we will see that psi 0 will also contain constants. So we can choose any value for f0 here. We could also set it equal to 1, because it does not really um, explain or give us some details about the solution. So it is not an important constant. And therefore, what we are interested in is in this equation. We are interested in this equation here, and we will start discussing it next time.